Hello Huskies, and welcome to Growing number 7. Our objective today is I can find decay factor and decay rate and use them to write equations. We're going to start right off with the classwork. We have at the very beginning of the classwork a graph and a table. I don't have the graph on here, but I did recopy the table. And we're talking about medicine. Medicine breaks down in your body using exponential decay. So we're going to try to look for the pattern here. We start off with a 400 milligram dose of medicine. Then an hour later, there's only 100 milligrams left of that medicine in your body. So what's happened is your body has used 300 milligrams of it, and you have kept 100 milligrams. So what's the pattern? If you were just looking on this table here, going down, it looks like you're dividing by 4, which we know is actually the same as multiplying by 1/4. So the pattern is multiplying by 1/4 because it's getting smaller every time, but it's not subtracting. We are multiplying. Okay, so then that's just the answer to number 1. How does it change from 1 hour to the next? It's multiplied by 1/4. Now let's use that to write the relationship. So what are we multiplying by every time? That's 0.25, 1/4. That's our decay factor. So if I'm going to write an equation, then I would say that the medicine is going to equal 400, that was my initial dose, the amount I began with, times 0.25 to the h for hours. And that is my equation. Now, I know this part is not on your classwork, but I think just to practice, let's say that if our factor, our decay factor, is 0.25, let's find the decay rate. Again, not on your classwork, but just to practice. If the factor is 0.25, then to find the decay rate, we are going to multiply that by 100 to turn it into a percent. So that would be 25%. Then we're going to subtract 100%. And so we get a negative 75%. That is our decay rate. And what that's saying is that we are losing 75% of the medicine every hour. Our body is using 75% of the medicine every hour. Okay, let's go down to number 4. We have a different medicine this time, and it breaks down at a rate of 20% per hour. That means that you are using 20% of the active medicine, and we want to first complete the table and then be able to write an equation. So if we think about this, we are using 20%. That means that we must be keeping 80%, or 20% is used every hour, and so 80% of the original or of the last dose must still be in our body. So then we can think of this as being a decay rate of negative 20%. And we're going to add 100 to that, 100%, and that gives me 80%, which is the same as 0.8, and that is my decay factor. If my decay rate is negative 20%, my decay factor is 0.8. And that does make sense, because if my body is using 20% of the medicine every hour, then I'm keeping 80% of the medicine. And so what I would multiply by every time is 0.8. And so we started with 60, and in the table you can multiply over and over again by 0.8. And so the very first line, after 1 hour, you would have 48 milligrams left, and then you would multiply that by 0.8, and you would get 38.4, etc., etc. So we would continue this pattern. And now to write an equation, the amount of medicine left in the body is going to equal 60, because that's what we began with, and our decay factor was 0.8, and we're going to raise that to the h power for hours. Okay, classwork on the back, number 7, you have another graph, and you're supposed to write an equation, but it's difficult to write an equation directly from a graph. So we're going to fill in this table. And I just went ahead and estimated some points from my graph onto the table. It looks pretty obvious that when x is 0, that the temperature was 80. And so then I kind of thought, well, maybe after 1 hour or 1 minute, the temperature would be 72 degrees. Sure, that makes sense. And kept going. And now that I have a table made, I can use that to write an equation. So the first thing I have to do is, what is the pattern? I need to find my pattern so that I can find my growth factor. And again, it's very difficult to be able to look at this and just see it. I don't expect any of you to do that. So we're going to take the second term and divide it by the first term. And then we're also going to take maybe like the third term and divide it by the second term and see what we get when we do these fractions, these divisions. So 72 divided by 80 equals exactly 0.9. Hey, that sounds decent for a growth factor, or decay factor actually. Let's check 65 divided by 72. Well, that's not the exact same thing. I got 0.9027 repeating. But if you look back at the equation, or at the instructions, it says, given the graph of this relationship, approximate the decay factor. Now, this has to be an approximation because this is like a real-life situation where we just wrote down the temperature every minute for 10 minutes, and we could have some variables that make us not quite accurate. Remember, this is like from an experiment. So this is going to be an approximation. So if you just did one more check, if you just did maybe 58 divided by 65, you would get 0.89. Well, actually 0.892307. Okay, so the point is, all three of these numbers are pretty close to 0.9. So I think we could say that if we were going to estimate, our factor would be 0.9. It looks like we're multiplying by around 0.9 every time. So then if I was going to write an equation, I would say that I would begin at the very beginning with 80 degrees, and I was multiplying every time by 0.9, and I'll give it an exponent, and that sounds good to me. Okay, on your homework, again, we're talking about medicine, and we're talking about penicillin this time with an initial dose of 300 milligrams. 1 day later, we have 180 milligrams left. So if we wanted to know the decay factor, we would have to take 180 divided by 300 to find out what we had been multiplying by. And that gives me 0.6. So my decay factor must be 0.6. That's what I'm multiplying by every time. And so, of course, you could use that to fill out your table. We already know the first two, 300 and 180, and if you continue to multiply by 0.6, you can fill in the rest of the table. Now let's write an equation. M is for medicine, and that is going to be the initial dose times my decay factor to the D. I was going to make an H, but I think it's a D for days. And that is just basically it. As soon as you find your decay or your growth factor, it's very simple to write an equation. Now, what would be the equation if you had taken a 400 milligram dose? Does the amount that you are dosed affect your decay factor? It does not. You would still just, or would it? Well, I guess it depends on how you interpret this question, because if you took a 400 milligram dose and you're assuming it's the same decay factor, then you would have 0.6 to the D power. But if you took a 400 milligram dose and there were only 180 milligrams left after 1 day, you would have had a different decay factor. And so that would have been maybe 400 times 0.45 to the D. I'm actually not going to use that one. I'm going to just assume that this penicillin decays at the same rate. And so we'll use this one. Okay, Number 4. You've been given 5 equations, and you're supposed to decide which represent exponential decay and what is the decay factor, or does it represent exponential growth, and what is the growth factor? So looking up there, I can see that I have 4 exponential equations and 1 linear equation. So I'm going to go ahead and start right off with the one that is not growth or decay, and that must be C. Why is that neither? Well, because it doesn't have an exponent, so it's not exponential. That's a linear equation. So C is linear, that is not growth or decay. And so now let's look back at the 4 that we have left. And remember that if it's growth, then it's going to have a factor greater than 1. If it's decay, it will have a factor less than 1. So growth, I see a factor greater than 1 here and here. So it looks like D and E are growth. And then we were supposed to give the growth factor for each equation. So the growth factor for D is 1.25, that thing in the parentheses. What are we multiplying by every time? And the growth factor for E is 2.5. So what's the decay factor for our 2 equations that are left, A and B? The decay factor is 0.75 and 0.25, that thing that you multiply by every time, the common ratio. That's our factor. Lastly, I just want to review for number 5, how do you turn a decay rate into a decay factor? If our decay rate is 20%, we have talked about how we should think of that as a negative 20%, because I'm losing 20%. And then I'm going to do the same steps that I had done turning a growth rate into a growth factor. I'm going to add 100%, but because my rate was a negative, this time the answer will be less than 100%. When it was growth rate, we got a number more than 100%. So if I am losing 20% of something, I am keeping 80% of it. And if I were to divide that by 100 to just write it as a decimal, it would be 0.8. And that is my decay factor for number 5. All right, I hope that helps you complete the rest of your homework. Good luck.